one of the fundamental concepts in chemistry is that everything is made out of atoms. Now, this is still classified as the atomic theory, and we'll talk about that here in a little bit. One of the reasons for this video cast is to look at the human endeavor on how scientists, and some that were just Greek philosophers, came up with this idea of nature's basic particle and the idea of an atom, how it got its name, and then how we discovered even smaller pieces within the atom, what it is made up of. And these are things that we couldn't see, yet we still based an entire scientific field on the existence of atoms. So I have this presented in the form of a timeline, because a timeline is going to represent key events within a particular historical period, arranged chronologically. So I want you to see what's going on in the world. You have your history classes along with this development of the atomic theory. Now, it is a theory, and I do need to make a distinction here. Now, theory is a unifying explanation for a broad range of hypotheses and observations that is supported by testing. And not just one test, many different tests by many different people. It has to pass that power of prediction. Some people misunderstand what a theory is, especially when you talk about scientific laws versus scientific theories. Scientific laws explain how something happens under specific conditions. Law of gravity. If you throw something up, it is going to come back down. Scientific theory explains why something happens. Scientific laws did not start out as theories. Again, laws classify how, and theories attempt to explain why. And that is the major difference between those two things. Both have been tested by many different people in many different places and had to pass that power of prediction. And we're going to talk about the atom. Now, it's the smallest particle in which an element can be divided and still be the same substance. An atom of carbon is different than an atom of oxygen. You break it down further and into protons, neutrons, and electrons. You can't really tell a proton from a carbon from a proton of an oxygen, only when they're in this thing called an atom. Okay, we're going to start way back in time, 440 BC. This guy was not a scientist per se. He was one of the Greek thinkers, Democritus, and he sat around and thought about things. And one of the things he thought about was that nature had this basic particle for everything, and he decided to call it an atom. That was the Greek atomos, which just means uncuttable. So this was that basic particle that you could not split, and that's as far as he went. Now, there were other Greek philosophers. You've probably heard of some of them. Aristotle is probably the one that you have heard of. And he was a contemporary of Democritus. And Aristotle said, I don't think so. God would not have done that. He makes people out of people stuff and plants out of plant stuff. There is no basic particle. And because Aristotle had greater clout in the community, everyone believed him, and Democritus's idea of the atom was put on the back burner for quite a while. So we're going from 440 BC all the way to 1803. So when I say a while, I mean a while. 1803 came along John Dalton. He's a British chemist and school teacher. He started off being interested in gases and worked a lot with gases, and you'll see a gas law from him later on in the semester. And he did what most teachers are really, really good at, and that is taking ideas from others. He said that we have these basic laws that we agree upon, the law of conservation of mass, the law of multiple proportions, which means that if two atoms are going to combine to form two different compounds, they're going to go into small whole number ratios, which means you're not going to have half an atom or 3/4 of an atom. And the law of definite proportions, which means that you're going to have the same percentage, like a salt crystal is 66% chlorine, 33% sodium, no matter whether the crystal is as big as which comes out of a salt shaker or a giant salt block. You have the same percentages, and so that's definite proportions. The proportions are definite. And he said if we agree that all these laws are true, and everyone did, then we cannot explain them without the existence of atoms. So he's the one that brought atoms back to the forefront. And he came up with the first atomic theory. And there were three tenets to his theory. Now, this is a little summarized, but he said that all substances are made of atoms. Atoms are small particles that cannot be created, divided, or destroyed. And again, that created or destroyed sounds a lot like the law of conservation of mass. Now, at the time, we did not know that we could divide atoms. That came quite a bit later, but that is part of his idea. Remember, atom means uncuttable. He said that atoms of the same element are exactly alike. Now, we have since found that that's not quite true. There are certain things that are alike, but there are also some differences that elements can have and still be the same element. But atoms of different elements are different, and that we still hold to be true. Atoms join with other atoms to make new substances called compounds or molecules. All right. We jump almost 100 years to 1897, and we have scientists. Now that we have this idea that there are atoms there, we still can't see them, and we don't know what these atoms are made up of anything. Dalton saw them as just these solid spheres, so we had some other scientists that were working on this theory. Now, by the late 1800s, we were really good at making glassware, and we could make them with extreme accuracy, and it allowed for more scientific testing to go on because we could take accurate measurements. In 1897, J.J. Thomson was working with a cathode ray tube. Now, these are the tubes that are in the back of old TVs. When he plugged one of these, and it only has a gas and it's sealed up. When he plugged these cathode ray tubes into a battery, he saw that there was a glowing light. And it seemed to move from the negative side to the positive side of this cathode tube. And he wondered, what is this that is glowing, and why is it moving this way? He hypothesized that since it was moving toward the positive pole of the battery, that it was a negative thing that was being attracted to that positive. So he said, whatever it is, it's probably negative. And then he went on to test that theory, or that hypothesis. So if we look at this, you can see he took some magnets and put them up next to the cathode ray tube. And you can see the beam of light. This must be a negative. And so the negative pole of the magnet is pushing the beam away from it. Like charges repel and opposite charges attract. So he said it was negative, and he called it a corpulus, but we know them as electrons. Another important thing that Thomson did is this changed our idea of the atom. Remember, Dalton said it was just a solid sphere. Well, because he discovered these pieces, Thomson decided that it looked like plum pudding. Now, you can't see it from here, but plum pudding model is what his is called, and that is the technical name. And that's pudding with plums in it, if you didn't know what plum pudding was. Probably a contemporary example would be chocolate chip cookie dough, where you have this big blob of positive stuff, and that would be our cookie dough. And the electrons are like the chocolate chips, and they can be added or removed from the particular atom. So it's a plum pudding model. Go ahead a little over a decade, 1909, we have Millikan here, and his experiment involved, it's called the oil drop experiment, and so he had some oil and had it so that he could spray out tiny, tiny little droplets of oil. Now, if you see here in the red, you've got some charged plates, and he knew the exact charge on these plates. He gave the oil droplets a little bit of radiation just to kind of give them a little bit of charge, and he had a viewing microscope here. Because he knew the charge on the plates and could measure the size of the droplets, He was actually able to calculate the mass of an electron, and that's going to be pretty impressive here. I'll show it to you in a second. He was also able to confirm that it is negatively charged. So the mass of an electron, 9.11 times 10 to the negative 28 grams. So that's a decimal point. 27 zeros and then a 9. That's how many grams an electron weighs, and that is a tiny, tiny amount, even compared to protons and neutrons. 1911, we have another important player here, Lord Ernest Rutherford, and his experiment is called the gold foil experiment. You can see a little rundown here. I'm going to show you a video here in just a second. What happens here is we have an element that produces alpha particles. Those alpha particles are shot at a piece of gold foil. Now we use the gold foil because it can be made atoms thin. So we had a really, really tiny, thin piece of gold foil. Now because he was operating off of Thomson's plum pudding model, he hypothesized that the alpha particles should go straight through that gold foil. And the screen right here that's around it in kind of a semicircle, this is a screen to let him know where the alpha particles actually went. You can think of them like an old film negative, and it showed where the alpha particles were. So if we look at his experiment here, got a little video.
In 1910, were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
Okay, so that gold foil experiment, most of the particles, alpha particles, did go straight through. And so that led Rutherford to conclude that the atom is mostly empty space. But some of the particles were deflected and with a really high angle, so they must be hitting something. Well, Rutherford thought about it, and he came up with an idea that what they're hitting must be that a small, dense nucleus in the center of the atom. And he came up with, and so he discovered the nucleus. And that was that positive stuff that the electrons are attracted to. Now we get to 1913, so we're here on the edge of World War I. We're still kind of discovering what an atom is. We have Niels Bohr, and he came up with a model of the atom, a complete model that had that nucleus, that had the electrons. And he said that the atom worked like the solar system, where you had the nucleus, would be like the sun, and then you had the electrons orbiting that nucleus like the planets orbit the sun. We have found that to not be true. It did not pass the power of prediction. We could not predict where the next electron, or where an electron would be when we tried using this model. It did work for hydrogen, but for no other element whatsoever. One of the important things about Niels Bohr's model is this idea of energy levels. And I think in probably some of your other science classes, you've talked about putting electrons in energy levels. Now, energy levels are distances from the nucleus, and they are always numbered from the nucleus out. So the energy level closest to the nucleus would be energy level 1, then energy level 2, energy level 3, and then you work your way out from there. And that is the part that we still use from Bohr's model of the atom. This is often is used to mean sciencey stuff. This is Bohr's model of the atom, and where you have these electrons moving like trains on a track around that nucleus. So it is completely incorrect, but for some reason we continue to use it in clip art and things like that. All right, 1914, at the beginning of World War I. Henry Moseley, studying with some of these other scientists, were able to discover the proton. It was positively charged, and we found that that is located within the nucleus. Now, if you look at this time period, from about the turn of the century, and then my last one here is at 1932, we had World War II starting, and not too much past this, 1939. And toward the end of World War II, we did drop 2 atomic bombs on Japan. But look at it in context here of the timeline. We only knew that there were atoms before 1897, and we didn't know what exactly was going on within an atom completely until 1932. Yet, by the end of the war, we were able to not only drop 1 bomb, but 2 bombs. So this field, this study of chemistry and atoms really went very, very fast, and we were able to not only understand what was going on here, but actually use and harness the energy, unfortunately to make a weapon, but that is what we did, and it worked quite well. 1932, James Chadwick discovered the neutron, which hangs around in the proton inside that tiny, tiny little nucleus. Now, there was quite a bit of time to find from 1932. It was our last subatomic particle that we discovered. The reason why it took so long to discover the neutron is because it does not have a charge. The others, positive and negative, we could manipulate that with opposite charges or with like charges and have them deflected. The neutron, it has no charge, so it was quite hard to detect. But we did, and by 1932, thanks to Chadwick. So this is kind of how we see the atom today. We see that there is this tiny, tiny little nucleus. Now, I've heard this explanation before, or this description. If you take an atom and you blow it up to the size of a football stadium, stands and all, then the nucleus would be about the size of a dime in the middle of the field. That's how tiny it is compared to the rest of the atom. And all of the protons and neutrons are located within that nucleus. And we're going to find that's where all the mass is located in a nucleus, is inside the nucleus as well, with protons and neutrons. The electrons exist in this fuzzy region outside of the nucleus, and we call that the electron cloud. The cloud is separated into energy levels. Here you can kind of see this first little ring, and that is our first energy level, and then the second energy level would be out here. And they're zooming around. We'll be able to describe the most probable region, but not exactly where that atom is going to be here in the next couple of weeks. So that's a little rundown on the atomic theory.